reinforcement learning with offline, basically offline reinforcement learning. I would like to start with like a bit introduction. Today's lecture is mostly about some introduction about the concept and some of the recent research which has been done on this topic. I would like to first start by the question, what is offline RL? This sounds a bit maybe strange, the combination of offline and reinforcement learning, because reinforcement learning is naturally an online algorithm. So if you look at the Wikipedia page, it says basic reinforcement learning agent AI interacts with its environment. So basically one of the main requirements for RL is that it should be online, and basically to choose actions and then be able to change the status of the state of the environment. But anyway, this is reinforcement learning, and reinforcement learning itself is really good, it's fantastic, but there are some properties that makes it even more interesting and attractive if we can also extend it to offline situation. So here's a visualization of what I mean of offline versus online RL. So as I said, in online reinforcement learning, we expect the agent to interact with its environment, perform action, and change the state of the environment, receive rewards. So this is what we are basically talking when we're talking about reinforcement learning. But today I'm going to talk about a completely different paradigm in which we are only allowed to learn from a data set of pre-recorded state action transition. So this is a very challenging problem, and it is very different from regular reinforcement learning. But is it? So I'm going to try to answer this question today. Let me start with what sort of data set we are talking about when we're saying that we are supposed to learn from a fixed pre-recorded data set. Here I just provided some examples from a data set called D4RL. And here in this data set, we have different kind of environments, different data, and then we are basically looking for a very specific kind of behavior. Here's an example for maze 2D and ant maze. So as the name suggests, the task is to solve a maze. For the ant maze, we have a ant robot that has to walk from one point to another. But for the maze 2D, it's like we don't care about the locomotion part. It's more about the navigation. So in this data set, for example, we may have trajectories already provided in the data set, how to move from 1 to 2 or from 2 to 3. But the question is that, can we use this offline data set without any possibility to interact with the environment in an online way to learn behaviors that would require to move from 1 to 3? This is a very challenging problem, but still we're interested in applying reinforcement learning approaches to also learn from such settings in which we don't have the opportunity to interact with the environment anymore. Here's another example. I just try to give a few examples about what you can expect from D4RL. This adroit environment. Here, the interesting thing about this is that we have a human demonstration. I think, yeah, it includes motion captured human data and realistic high degree of freedom robotic arm. So the interesting thing here is that we have expert data recorded by humans, and we would like to basically learn the demonstrations that are provided by humans. This problem is also known as learning from demonstration. And in case we expect high quality expert data in the data set, This problem has been previously solved by, let's say, calling it behavior cloning or imitation learning. But the interesting thing about this setting is that we're not always provided expert data. We can basically, let me go to some other environments. I guess this is the case. For some of the case, we don't necessarily have access to high quality trajectories. We sometimes only have access to data which is used, which are generated during another oral training session. So it does not necessarily contain high quality demonstration in this setting. So when we sometimes have to also learn from data sets that include also low quality data. And the question is that, can we do better than, for example, behavior cloning for this kind of setting? I haven't still answered why offline ORL. I just try to give a very brief introduction about what offline ORL is, but why are we interested about offline version of reinforcement learning? The first answer to this question is the success that we have observed from computer vision and natural language processing problem domain. So the thing that made it possible to improve computer vision problems or solution to computer vision is one of the main reasons is the existence of diverse and basically big data sets like ImageNet. And the same thing is also true for NLP. So for example, in BERT, we also try to learn from a huge amount of data. So this offline data plays a vital role for computer vision and natural language processing. But still, we don't have such possibility in reinforcement learning, because in reinforcement learning, typically it's hard to learn from an offline pre-collected data set. And this is why we're interested in offline ORL. So that's one reason. The second reason is that with reinforcement learning, we typically can't share data among ourselves. So, and more interesting is that if I collect myself some data today, I typically can't use them the day after. So that is a big problem. We can't share data, let's say, within universities, research institutes. We can't reuse the data that we have collected before. And we already know that this data exists. I mean, you can have a look at, I just tried to provide a few references like BCZ, RoboNet, and Bridge dataset that contain a lot of robotic manipulation. And the question is that how can we reuse the data that are provided by other data sets? And if we, for example, want to create another data set that, for example, from our own oral training sessions, what kind of properties do we need for these data to be reusable? These are the questions that we typically try to answer using offline reinforcement learning. But there's also another important advantage of offline ORL, and that's in robotic, but I guess this is true for many domains. Whenever you want to do a control task, typically you would have some safety constraint. You're not allowed to apply to run a trial and error oral exploration on a real robotic platform. Or even, let's say that you're controlling the temperature of, let's say, some housing, and then you can't really let the oral agent to just randomly increase or decrease the temperature. So we need to ensure some sort of safety when we're doing reinforcement learning, because we're working with real physical systems. And one way to ensure safety would be to train a policy based on offline data, because we can collect this offline data once, we can then be sure that we do the data collection in a safe way, let's say through human demonstration or using the controllers that already are in place. And then we can use this data for our policy training purpose. So these are some of the reasons that why offline reinforcement learning is very interesting to us. But then the question is that you may already think about that we have off-policy reinforcement learning. And to some extent, there are some similarities between off-policy and offline reinforcement learning. Because in off-policy algorithm, we also expect the policy is, the data is collected from a different policy, and we are updating another policy. And these two policies, the policy which is used for data collection and the policy which is updated by the data, do not necessarily need to be the same. I would like to first explain that off-policy algorithm, they exist for many years, and to some extent you can already apply them to offline learning. But before going into that direction, I would like to provide some details and make it clear what is the difference between online off-policy and offline ORL. And these slides are, these pictures are borrowed from the paper that you see on the upper right of my slide. And I really recommend you to read that paper. This is actually a tutorial. And some of the materials that I'm covering for today comes from this tutorial. So let's start with online reinforcement learning. For online reinforcement learning, we're assuming that, okay, we have basically two phases. One is the rollout phase. We are trying to make rollouts from the policy by interacting with the real world environment. And then once we have collected our rollouts, we update the policy. And then the updated policy will be used in the next iteration to collect more data. In off-policy reinforcement learning, things are slightly different. Basically, this is not really offline, or we are not, I mean, it's not very true to say that we are really using a different policy. In the existing off-policy algorithm, we typically use the same policy that is used to collect the data and the one which is updated. They're mostly the same. The big difference here is that whenever you make some rollouts, you put them into a replay buffer, and then you reuse the data in the buffer to update your policy. So in a sense, you can say that the data comes from all the policies from iteration 0 to iteration K, and these are the policy used to collect the rollouts or the data. And then from this perspective, the policy which is updated is different from those policies which are used to collect the data. And finally, we have offline reinforcement learning. So this is truly offline. We're assuming that the policy which is used to collect the rollout is completely different from the policy which is being trained. And here, we're assuming that, let's call it a behavioral policy. This behavioral policy can be like a human that is just trying to provide the demonstration to a robot or to an agent. And this data is collected and put into a data set. And then once we have that data set, we can basically reuse the data in the buffer to train a completely new policy. All right, then let's see why existing actor-critic oral algorithms are not able to learn from offline settings. Okay, here again, the picture of the offline setting. We're assuming that we have a data set that contains state, action, transition, and reward. So now we would like to update we want to train an actor critic policy or using actor critic methods to train a policy. So we have two steps here. There's a typo. One should be critic update. The other should be actor updates. They shouldn't be critic. Sorry for that. And by the way, you may notice a lot of typos and inconsistency in the notation of my presentation. I'm very sorry for that, but I was working on a deadline last night, so didn't have time to really fine tune my slide. Okay. So as I said, for actor critic reinforcement learning, we have two different update rules. The first one is the critic update, in which we use Bellman operator to update the Q function. As a reminder, a Q function or action value function is basically, it's mathematically defined like this. And basically it means that if you're at a state S and we apply the action A and we follow the policy to collect the rest of the trajectory or rollouts, what would be the expected reward or discounted reward? This is the discount factor. Discounted reward that we should expect from this state and applying this action. So this is the definition or reminder of what an action value function is. Okay, let's go back to the critic and actor update using offline data. So the problem is that, first of all, S, A, and S prime, they all come from the data set. So which we call them in distribution because they are coming actually, they're sampled from the data set. So we don't have any out of distribution problem or distributional shift on those data. The problem is actually here. For the update, we need to first, we need to understand what would be the value of the next state and the action that we're supposed to take under the policy. So here is where we have a problem because this policy can just give us a random action, and this action is not in distribution. And because of that, we may overestimate the Q value for that action. And remember, the policy itself is optimized by maximizing, by finding actions that maximize the Q function itself. So therefore, actions that are basically found by argmax, they can be a problem for Q learning updates because they can easily create out of distribution problem. And because of the distributional shift, then your the estimated Q value for the next state and action can be completely wrong. And based on that wrong value, you may update your current state and action, and this error can be accumulated. And at the end, this can destroy the training of the Q function. So this is the problem.
Hey, Ali, may I ask a question here?
Sure, please do.
So when you mention in and out distribution, when you mention out distribution, is it because of like we didn't collect data, or what could be the out distribution?
The out of distribution comes from the fact that the Q function is queried on an action, this action, which may not be in the data set.
Yeah, so that means we didn't observe this combination in our data set, so we don't know the distribution of that.
Exactly, we don't know what is the reward. And because of this, we may experience distributional shift, and that can, would over time basically cause accumulation of errors. And at the end, we may not be able to evaluate the policy using Q learning.
Thank you so much. Yeah.
Thank you. Is there any other question here? All right. So to address this problem, we have some options. One of the options is called policy constraint method. The basic idea with policy constraint method is that we would like to constrain the policy that we are training here to stay as close as possible to the behavioral policy. So remember that the problem that I mentioned in this slide is simply that this policy can produce actions that are out of distribution. So, and then the solution can be to constrain the policy not generating actions that are out of distribution, or in other words, try to make sure that the policy generate actions or action distribution, which is as close as possible to our behavior policy. This is basically the general idea behind policy constraint methods. I'm going to show one specific example of how this policy constraint approach can be formulated. One way is basically to enforce this penalty term both at the Q level and also at the policy level. So here you're trying to subtract a basically subtract the distance between the distribution given by your policy and the behavior policy. This would ensure that you're not overestimating the value for out of distribution actions. And remember that overestimation is a problem in Q-learning because we are using the argmax operator. And if we have a wrong maximum value, this can be accumulated over time. So that is why one way to alleviate this problem would be to enforce a penalty term into the Q function so that we are basically kind of underestimating the true value for the state and action pair. And at the same time, when we're doing the maximization over the policy, we can also make sure that the policy does not deviate too much from the behavior policy. There is a problem in this formulation, and this is that you have to explicitly model the behavior policy here because you need to, this formulation depends on a distance measure between the distribution found by the policy and the behavior policy, and as a result, this would require to model your behavioral policy. And one way to do that is through behavior cloning. So by using that, you can learn an explicit behavior policy and then use this formulation in order to learn a behavior from offline data without deviating too much from the behavior policy. Is there any question here?
Yeah.
Yeah, me too.
Please go ahead.
You can go ahead first.
Okay, so my question is that, so what is the difference between this one and imitation learning? Or is it better, always better than the imitation learning? Because the penalty part, somehow I feel like it's close to the imitation learning. You just imitate what the behavior is. And then somehow it also have a RL flavor to trying to learn the policy to optimize the reward. So, yeah.
Yeah, that's a very good question, actually. So there's like, we want to make sure that the policy training is somehow done in a conservative way, which means that we don't want to deviate too much from our behavior policy. So naturally, this means that on one end, one extreme end, we can go to behavior cloning. So let's say that if we enforce this, if we have like a very large alpha here, then basically we are somehow forcing just, we're giving high values, I think, only to the policies that are as close as to the behavioral policy. And here, if this alpha is so large, then you may completely ignore this part and only try to minimize the distance between the policy and the behavioral policy. So as on one end, the extreme case, your policy may become very, very close to your behavioral policy. This is not what we would like to happen because of several reasons. The first reason is that we would like to have real benefits of reinforcement learning, which is basically it tries to also explore and find more appropriate actions. So behavior cloning, you're just trying to reproduce whatever given by the data. But here, you're also trying to maximize the reward, and possibly you can find more appropriate solution than behavior cloning. And most of the experimental results that are shown by different papers from offline RL area, they always compare to behavior cloning and show that their approach improves performance over behavioral cloning. But there's another important aspect to this, and with behavioral cloning, we always assume that the data that we have access to, they're optimal or suboptimal somehow.
Yeah.
And we can't really learn from random data because there is no, basically, it's not possible to behavioral clone a random policy. And there's no point in doing that. But still, with this formulation, we are still able to learn from, even if the data is not of high quality.
Thank you. Very good point. Thank you so much. So like a following up question, if we think from like a meta learning perspective, so somehow eventually we'll apply our policy like in the real world problem. So then I guess this policy constraints method, they can be initialized better than the behavior clone methods, I guess, right?
Right. I'm going to talk about a little bit more about this aspect. And especially when I start talking about generative models, then this is also something that I would mention.
Excellent. Thank you.
No worries. And hopefully regarding meta reinforcement learning, I will talk about it in our next lecture. So slightly different topic. But anyway.
Thank you.
Yeah, thanks for the questions. Is there any other question before I can?
Yeah.
Please go ahead.
So am I right in understanding that this policy constraint method basically implicitly imposes a ball around the behavior policy within which the resulting policy that reinforcement learning acquires will be in? In that case, my question is, doesn't that place an assumption that there is some kind of continuity such that near the behavior policy, the data is, the information that we have is well behaved, so the reward is in some sense lipsage or what have you? Is this always a good assumption to make?
That's a very good point. And of course, yes, this is the assumption there. That depends. Honestly, if this assumption is not true, then you may have difficulty even with online reinforcement learning. So you're always trying to assume that there is some sort of structure which makes the reward function, let's say, continuous. And yeah, this is something that we most of the time consider. And here for this particular example, definitely this is required, because otherwise the only thing that you can do is to just do behavior cloning, and you can only learn some behavior at exactly same points that are there in your data set, and you can't really interpolate or extrapolate in any way.
But then my question is, isn't it better to simply impose a restriction on the behavior policy such that it sufficiently explores the environment? Because it feels like this is a patchwork approach to compensate for a bad exploration policy.
Basically, this is already here. You know, if you look at this second, the part we do the actor update, we're already trying to penalize the policy from deviating from the behavioral policy. So this is already there. I guess the reason
Yes,
for
this
having
deviation is such that your resulting optimal policy will be close to the behavior one.
yes,
But how this behavior policy was generated, there is no assumption stated on it. So if this is a very bad behavior policy that does not explore the environment, it feels like this entire algorithm will be useless, like whatever you do. So there must be an assumption on the behavior policy that it sufficiently explores. And is this typically done? Is there like a standard assumption placed on this behavior policy?
That's also a very good question. And that's why I started my presentation talking about D4RL, because basically, as I said, we can't only expect that we have been provided a data set. We have to also understand what property we need for the data set itself to be able to do offline reinforcement learning. And I was talking to Ilya last night. He is a researcher from Berkeley, and he was mentioning that basically his main research is about also generating this kind of offline data sets. And he was just describing that, for example, what kind of problems do we have with existing offline data sets like D4RL? So that's a very important point. This is a topic by itself that was doing a lot of research to understand what properties and the data set should have. And by data set, of course, I implicitly mean the behavioral policy, because the behavioral policy is the one that constructs the data set. So yeah, this is, I completely agree with you on this. And we have to be sure that during our data collection, we are also making sure that we produce good quality data that does sufficiently well exploration to learn some good behavior using offline RL.
Okay. Yeah, thanks for your comments.
No worries. Thanks for asking. Is there any other question before I can move on?
I was wondering kind of the opposite, that if your behavior policy is completely random, what does that imply when you're taking when you have this optimization constraint that you're trying to be close to the behavior policy?
Remember that it doesn't mean that, you know, okay, there's something very important that I have to make it clear now. Even if you have random data, if you train a behavioral policy on that, of course, you can't learn anything meaningful, because then it will just perform randomly. But it doesn't mean that if you constrain being close to the behavioral policy at the state S, means that this learned policy also behaves randomly. You can still learn a meaningful policy that tries to solve a task by just constraining that the action distribution at a state S should be as close as possible to the behavioral policy. So it's only about state S. So at this state, we don't want to explore the states that I've never seen before. So they can be like a very unsafe state. They can be, I don't know, we don't want to explore actions that are not seen for that particular state. And that is like just, this is the only constraint that is imposed here. And again, it doesn't necessarily mean that this constraint would make your policy also random. Is it more clear now?
Yeah, a bit. But I think, yeah, you are right that the state is the important part here and not the action. That is what we're conditioning on.
Yeah, so conditioning on a state mean that let's say that we're talking about an image, a like image-based reinforcement learning, and in that particular case, an state is like a visual observation. So condition on the image that you see at the current time step, then the robot probably can do certain kind of actions. Let's say if the robot see a wall, then most likely the robot should not go toward the wall and should not hit the wall because okay, first of all, we don't want our robot to have collision. And second of all, it's like an action that is dangerous. And most likely in our training data set, even if the agent performs randomly, we expect that we don't include any collision in our training data set. And as the result, the behavioral policy probably can just move randomly, but should not contain any action that would hit the wall. So that is my main point. The policy here, by not deviating from the behavior policy, means that it should not hit the wall because hitting the wall is not in the distribution, but it can choose different random direction to continue. And it chooses those direction based on the expected reward that is estimated using the Q function. So this is the mechanism that enables the policy to still learn and not deviating too much from the behavioral policy.
But sorry to
no worries.
We can continue if but like what you said there, that we are explicitly removing actions then that are illegal from our data set.
That are not in the data set. I mean, illegal probably.
I mean, because as you said, like we don't want the robot to crash into the wall. So, but the random policy would crash into the wall because it's random.
That is the point. It can be random, but it's probably there is some supervision. Let's say there is like a human operator randomly moving a robot, but the person never crashes the robot to the wall. So that is the difference. So yeah, sorry, I didn't make it clear. It's not random in a sense that it can contain any action, but it's random in a sense that probably doesn't have any target task. So by a target task, you can say that I want to go move to the point A. That's like having a target task. But if you don't have a target task, you can just randomly wander around and this is like a quite random behavioral policy, but without any task.
Okay. Yep. Okay. I would maybe use, yeah, I would not use the word random in that case, but I get your points.
Right. Yeah, of course. I mean, typically we don't use the random word here in the context of full RL, but I just wanted to emphasize the fact that the extreme case that behavior cloning cannot work at all because there's no pattern in the data. But on the other hand, the policy being trained can still learn something meaningful. That's why I use the word random, but I wanted to use it to just show the extreme case, not something which is very typical when you do offline RL. Great. If there's no more question, I can move on to the next slide.
Here, but what you can say maybe is that in the behavior policy, you don't have any restriction at all, or you don't have walls. You can say, instead of saying that you have walls and then it's random except the walls, maybe you can say there are no walls, there are nothing, there are no targets and no holds in the behavior management policy. And then in the other policy, then you put targets and you put walls. That's maybe the difference to see the example or the comparison.
Right.
Maybe, I don't know, just.
Yeah, good point. But again, you know, typically you assume that the tasks are the same. I mean, not necessarily again. But of course, that can be one way to also collect the data. But again, you have to be very, I mean, just collecting the data itself for offline training is a topic worth having a lecture about it. And as I said, I'm in contact with people that their responsibility as a researcher is mostly to create this data set. And so it's not something trivial.
Yeah, no, what I meant is that in order to explain it, when you explain it, in order to avoid confusion about what random means, because the previous Jakob, I think it was, he made a very valid point. I mean, if it's random, then it should hit the wall. It should be, everything should be everything goes. But if you want to make a point that is not random, it's completely, then you can explain it.
Right.
I'm just making the point that maybe you can explain it that way. That you can assume that the walls will never be hit it because there will be no time for the data set to contain that action. The walls will be very far away or something like that.
But
Just
there is a technical problem with that, because you really want to have the wall and show the robot that in this state, you're not allowed to hit the wall.
Okay.
You're allowed to take an action. This observation, this state should already be there. Otherwise, during the deployment time, this states with walls comes out of distribution to the learner, and again, it would fail. Even if you just do whatever I'm talking about here. There's another research that we did recently. Actually, this is the topic that we submitted to the IRS this morning. And there we're talking about a mechanism that would enable you to still do well for out of distribution states. But anyway, the topic that I'm covering today actually does not talk about how you can cover out of distribution states as well. So it's only about out of distribution actions. So, but maybe it was like a very good point that I should not really use the word random. I guess the fact that I used random created this confusion. But I just wanted to make the point, like make it a bit more extreme to show that, to tell that behavior cloning, you can't expect behavior cloning to work in those cases, because if it is completely random, then there's no information that can be learned by the behavior cloning.
There is no pattern. Yeah.
More clear now.
Sorry to beat on the dead horse, but then the original question was for the random policy. So for the truly random policy that is not in any way directed or blocked, this method, I guess, would be problematic depending on how you tune alpha, right?
Let me make something clear. Yeah. If a very random policy can work in the environment, then we don't have the safety issue. That is the first thing. But still, you can learn navigation skills to move from A to B. And even though the data that you've collected randomly do not have any information about how to navigate from point A to point B, still these very random data can be useful for moving from A to B if you apply this algorithm.
But from the last line, for me, it looks like it will choose the argument that maximizes this expression. And this expression is such that you are penalizing the value based on the distance from your random policy. So if you behave in a deterministic way, let's say, you go from A to B in a deterministic manner, depending on how you choose alpha, you could choose an alpha such that it becomes that the penalty dominates even the straight line, and then it will go to this from A to B in a pseudo-random way in order to conform with this penalty. Or that's how I perceive it when I read this line.
Right. If you choose alpha super large, this is what happened that you're saying, as you mentioned.
But only for pathological cases of alpha that are not typically chosen. I guess that's what it boils down to. You choose alpha small enough so that you avoid this.
Exactly. If you choose alpha correct, then you're still able to basically satisfy both constraints, the state in distribution, considering the behavioral policy, and also learning how to move from A to B.
But then to me, it looks like this might not be meaningful enough because if you choose alpha, there is a sweet spot for alpha where you have the safety and you don't have the penalty. And if you don't get that sweet spot, it will not do much for you in terms of safety. Or that's how I imagine it right now. Am I
It's
wrong?
not only about safety. It's also about learning something. You know, if you have alpha equal to 0, let's say, again, I'm talking about extreme case.
Yes, yes.
You set alpha to 0, again, there will be like a problem for learning because you're evaluating here. You're gonna evaluate actions that are out of distribution. And as the result, the Q function cannot be trusted. And as the result, then you may overestimate the value for SNA, and that will basically destroy everything for Q learning. So it's not only about safety. We're not concerned about
the
safety.
main selling point is the learning part, that you will learn more accurately if you have this penalty. Okay.
Exactly.
Thanks for clarifying it.
No worries. Okay, let me just continue because I guess, Chris, are you still here? Can I ask you how much time do I have, or do we expect a break in between?
I think it's mostly 2 to 3 30.
Okay.
So
I think we have 40 minutes left.
Okay, we have 40 minutes more.
something like that. Yeah.
Okay, let's see where how much of my slides I can cover for today. If otherwise, I can continue the rest of them for the next week. Now I'm going to talk about another approach. Again, still I'm talking about a policy constraint approach for offline reinforcement learning. So that's the topic for today. But now I'm talking about a different solution to this problem, which is called advantage-weighted actor critic. Before I go to details, let me remind you about Q function. I guess you already know about what it does. Value function is basically the expected, it's just doesn't take into account actions. So this can be viewed as like finding the expected of Q over all different possible actions. So that's the value function. An advantage function is simply the subtraction of Q and V. So this is advantage function. Advantage function is a very important quantity because basically the value of a state will tell you the expected return that you may get for this state, no matter what action you choose. But advantage basically tells you how good is this action considering the average performance that the average return that you should expect at this state. So this is basically a quantity that explain how good is the action in this current situation. So that's advantage function. So again, let's go back to our policy formulation, constraint policy optimization formulation. We can say that our policy can be found as an argmax of expectation over advantage function. The difference is not too much. Before we had the Q function, here we are basically using the advantage function. So that's to me not a major issue. And then again, we want to put a constraint that the KL divergence, here I'm talking about KL divergence. Before I was talking about general distance, but here I'm talking about Kullback-Leibler divergence measure that measure the distance between two distributions. here we're saying that we would like to optimize the policy by finding the argmax of the policy, which would maximize the expected of advantage values to the constraint that the KL divergence between the policy being learned and the behavioral policy should be smaller than a threshold. And the other constraint is that the integration over all possible action should be equal to 1. That's because it's a probability distribution. This is our advantage weighted actor critic problem formulation. Let's do a little bit of math here. To solve this constraint optimization problem, we're using Lagrangian multipliers. So by using the Lagrangian multipliers, lambda and alpha, the objective becomes like this. Then we find the derivative of the objective with respect to the policy pi, which would be like this. If we make this derivative equal to 0, then we can find the closed form solution, the closed form optimal solution to this policy constraint problem to be this guy. So which means that basically the optimal solution to the constraint problem is to weighting the let's say advantage weighting the distribution which is given by the behavioral policy, and then of course normalizing it. This optimal policy can be basically learned by a parametric function. Let's say this is our parametric policy being trained. This is like our main policy. And this optimal policy can be realized by a neural network policy by, let's say, minimizing the KL divergence. We can actually use a KL divergence to project the optimal policy to the parametric neural network policy like this. But this KL divergence can be simplified to this formulation, which means that you can, I'm sorry, you can optimize your parametric neural network policy without even modeling the behavioral policy, and that's excellent. So what I said before, we really need to do behavioral cloning to learn a behavioral policy, but this formulation does not require a behavioral policy to be learned. And here you can simply sample from the data set because, of course, if you sample from the data set, then you can assume that the data is sampled from the behavioral policy. So this is a formulation known as advantage weighted actor critic. Yeah, is there any question on this?
Yeah, I have a question. Would you mind introduce the previous differential equation a bit? Like, where is it from?
You mean this one?
Yeah.
Here you mean, I guess, right?
Yeah, yeah.
It's okay. We first remember that we converted the constraint policy optimization problem using by using Lagrangian multipliers, lambda and alpha. And now we can find the derivative of the new loss function with respect to the policy pi. And if you do the math, I guess it's not that difficult.
I see. So you compute the partial derivative and then you make it equals to 0, or?
Yes, equal to
Okay,
0.
then,
I want to find the optimal solution to
cool.
this.
Yeah. I get it. Thank you. Yep.
And this is the optimal solution. And which means that there's like a very interesting property here, which is like, if you look at here, we are updating our policy now with sort of supervised learning. And we don't have this actor critic, the actor update anymore. It's more or less like a supervised learning, but still remember that you have to learn the advantages, which would require a Q function and a value function. So that's still there. But if you only look at the final formulation for the policy optimization or actor update, it's no longer reinforcement learning. It's basically will be optimized by full information provided by the data, or supervised learning using the data that we have in a data set.
Yeah, that's cool. Yeah.
Do we have any question here? Great. Now let's revisit the solution that we provided for policy constraint method again. So we said that in order to learn from offline data set, one possible solution is to ensure that the policy and the behavioral policy, they're put close to each other, and which means that the policy does not produce out of distribution actions for that can destroy the policy evaluation step here. So far, I've just tried to explain two different approaches, how you can basically do this problem formulation. Now I'm going to talk about a completely different approach, which is based on generative models. Before I can go into details for generative models, I need to provide a little bit of background of what do I mean by latent variable generative models and how they're trained. So first of all, the most important thing is that we're going to deal with latent variable generative models, which means there is like, if this is the data that we are, now I'm talking about generative model training, unsupervised learning of to generate photorealistic images. So it's a little bit now not very related to offline RL, but you will find the link soon. So let's assume that our data are human faces. So we can assume that there is like a latent variable that is basically characterizes different properties that are in our generation process. Let's say the eye color, hair color, I don't know, nose, eyes, and things like that. So we can assume that there is like a latent variable that would decide about these details. Now our goal here is that we want to learn a model that maximizes the log likelihood of the data. Basically, we want to use this model as a generative process to generate new photorealistic images. The log likelihood can be basically, we can marginalize this probability over the latent variable, and then we can introduce a variational distribution Q. So far, nothing really happens. You can just cancel QZ from the numerator and the denominator. Then you can, I'm sorry, I just noticed that QZ should be QZ condition on X. It's not QZ. It should be QZ condition on X. And then basically, you can expand this term, and we can use Jensen's inequality to which would say that our log likelihood is going to be larger or equal than these terms, which we call them basically the variational lower bound of the log likelihood. And again, please note that this second term here is just a KL divergence between the variational distribution and a prior distribution, which is typically modeled, the prior distribution typically modeled by a normal distribution, zero mean normal distribution, this is that, and covariance equal to 1. Great. So now instead of maximizing the log likelihood of data directly, we can maximize it by through maximizing the lower bound, which is found here. This lower bound can be basically maximized in an autoencoder structure, such that you first learn an encoder that encodes the inputs data into a latent space, and then you can sample from that latent space to reproduce the input at the output again, The main constraint here is that the distribution over the latent variable z should follow a prior distribution, which is, as I said, is a zero mean and zero mean standard deviation, a standard normal distribution. This typically is called the variational autoencoder, and it's used to learn to reproduce input images at the output. Here is an example of how the decoder part, or the generative model, which is the one that maps Z to here images, can be used. So as you can see here, I was just trying to change the latent variable on 2 dimension. And as you can see, by changing the latent variable, we are able to generate faces that are, I mean, if the latent variable are close to each other, the faces are also close, but as you just walk from one side to other, you will see that you can generate very different kind of faces. So this is the way that your generation process is basically controlled by a latent variable Z. And we're going to use the same sort of generative models, but for our offline reinforcement learning problem setting. So how do we do that? First, as I said before, we assume that we have access to an offline data set. By the way, before I continue, is there any question about the generative model part? Okay, good. Then we're assuming that
just a little question.
Sure.
The previous, yeah, and that slide. Correct. I mean, I apologize if I'm very mistaken, but is it? It looks like to me that is the target. The target for the agent is to from one image to arrive to the second image, to the last image, right? Is something like that?
No, it's just
trying to learn how to get to the last image.
No, sorry.
In the row.
No, I just had to make it a bit more clear. The thing is that we are having a data set of different images, right?
Yeah. Mm-hmm.
We would like to learn a generative process which can generate new images not included in the data set, but still they should be as similar as possible to the one that are already in the data set. So this is our task. So our task is purely generation. We would like to generate new photorealistic human faces that possibly are different from the ones that are in the data set. And this generation process basically receives a latent variable Z as the input, and then it gives it to the generative model and generate an output, which is, as I said, should be like a human face in this particular example. And this thing that I discussed here is that how we can basically, by maximizing the log likelihood of this data, train such a generative model that would be able to map a latent variable Z to different human faces. And as a nice property of this generative model, you can see that, let's say, if I have a 2-dimensional latent space here, I mean, it's not a 2-dimensional, but let's assume for now, it's a 2-dimensional latent space here. Then if I have like my 0, 0 as a latent variable, give 0, 0 to the generative process, it will generate, let's say, this face. Mm-hmm. But if I just choose 0.1 and 0, then it will generate this, 0.20 this, and I don't know, 0.5 and 0 this. And on the other hand, 0 and 0.5 should generate this. So this is what I'm trying to say. If your latent variables are close to each other in the latent space, the faces that are generated should also remain the same. And again, I mean, still not really, I mean, this is a completely different problem formulation. I'm now trying to connect it to offline reinforcement learning. So far, I just provided a very rough background for how generative models should work in typical application.
Got it. Thank you.
No worries. Is there any other question here? Okay, cool. Let's continue then. So we're assuming that we have, again, access to a an offline data set, which contains the state, action, transition, and also reward for each time step. So the goal here is that given this data that we have here, we would like to learn a generative model. Again, I'm talking about the latent variable generative model. So there is like a latent variable, which I can sample. And by sampling the latent variable, my generative process should be able to generate actions here. And then once I have this generative process that can generate the condition on the current state, can generate some possible actions, then I would like to use that generative model and train a more high-level policy to regulate the output of the generative model. So here, if you look back again at my example for generating human faces, your generative model, basically, if you sample this latent variable, let's say randomly, you can generate different type of faces that you see in this slide. Here, and the reason is that it's been trained, the generative model has been trained by human faces. But if you now sample this generative model, then you would be able to generate different actions. And these actions are the ones that are in the offline data set. Why it is important? The reason is that, remember in my previous slide, I told this that here. I said that I would like to force the policy being learned to be as close as possible to the behavioral policy. And this constraint now is enforced by generating actions using a generative model. And this generative model is limited to generate actions that are in the data set. It can't generate something outside of the data set. And this is exactly the property that we were talking from the beginning. We would like to be able to constrain our policy being trained to stay as close as possible to the offline data. And because of that, now if we train a high-level policy on top of this generative model, we can be sure that our policy would only produce actions that are already in the data set or that are just close to the behavior policy. Is this clear?
Sorry. So basically, we can see it as the behavior policy is like the boundaries of the behavior that we're trying to optimize. Is the boundaries. It cannot go further in any way. It cannot go beyond. That's the beauty, let's say, of the behavioral policy. That's the goal of it.
Right.
Is that right? Is that correct?
Yes, this is correct. So again, I would like to emphasize that condition on this state that exists that is like here, I would like to only generate actions that are in the data set. So let's say if you have these states repeated, let's say 100 times, and in these 100 times, my data set contains, let's say 20 different, now I'm talking about discrete action space, but I guess it's okay. Then let's say this only contains 20 different actions, then this generative model is supposed to learn to generate these 20 different possible actions conditioned on that state. And when we are optimizing our high-level policy, this high-level policy, since is only regulating the latent variable, then it's only is capable of generating, basically testing or evaluating those 20 actions that are in our data set. And of course, doing this, we are somehow also interpolating between action, because at the end we're learning a model using neural networks, and there is of course some possibility for interpolation and extrapolation, but still this is a very good way to enforce the constraint that that our policy should not deviate too much from the behavioral policy. Maybe this is a good picture sorry, that tries to explain this situation in a bit more clear way. So that was how you can use explicit policy constraint algorithm to constrain your basically the actions of the agent to stay as close as possible to the behavior policy. So the green one is the behavior policy, let's say, and the blue one is the agent policy. So by using, let's say, KL divergence or MMD, you would like to limit your agent policy to stay close to the behavior policy. So that's the first category of algorithm that I just tried to explain. So what for using generative models, simply you train a generative process like here, and you are sampling latent action, from the latent space, and these latent values are mapped to different actions that are inside the set of action which can be produced by the behavioral pulse. So that's one big difference here. Is that clear what I'm trying to say?
One thing that I was thinking about, that if you go back one slide,
Sure.
the fact that A and R are with, or I guess only A is within this distribution that we are generatively producing, because I'm thinking about this, that if we at some point, like if you just generate the environment and you know the transition dynamics of that environment, then you could act upon that environment, like you're working on synthetic data. So I guess my question is, why are we generating actions here?
What you mentioned is actually, it's a very good point. One thing that we have to take into account here is that learning the dynamics of the environment is quite tricky. And first of all, the method that you're talking about, there are some methods that are close to what you just suggested, that they are called basically model-based offline reinforcement learning. One of the basically well-known approach there is called MOPO, model-based policy optimization, if I'm not wrong. And what it does, it tries to learn, given the offline data, it tries to learn a dynamic model that would predict how the state of the system would evolve, and then uses that dynamic model and a notion of uncertainty from the dynamic model to be sure that it stays inside the distribution. I didn't include model-based approach in my presentation today because I want to basically talk mostly about model-free. And there was a particular reason, and the reason is that learning dynamics model is particularly very hard by itself. So typically you can't really learn a good dynamic model from the data. And beside that, you need to also have a notion of uncertainty for your data, because we have the way that we would like to make sure that we are staying inside the distribution of the data is by understanding where the model is sure about the output. So this is the way that we do it. And therefore, we need not only learn a dynamic model, but the dynamic model should also be probabilistic, which makes it even more complicated. But on the other hand, if we restrict ourselves to the model-free algorithm, then we have to think about how we can be sure that our actions that we are taking during training to train our policy do not deviate from the actions that are sampled from the behavior policy. And as I said, there are two ways. One is explicit kind of constraining the action to be close to the behavior policy through, let's say, KL divergence and MMD. Another way is to use a generative process, and this generative process ensure whatever you generate, whatever action you generate using the generative process would create actions that are within the support of a training data set. Is that more clear now?
Yeah, but it is this idea that we are jointly jointly generating both the environment and the policy, because it's generating both states and action. It's generating state action pairs.
Yeah, but that's a difficult problem, especially when you have limited data, because for generating the states, you have to, given current action, current state, you have to generate the next state.
But isn't that what the definition you just showed? It has an S prime in it.
The data set contained the S,
Yes.
A, and S prime. So of course, so this information is already in the data set. Let me see if I have it somewhere else. Okay. But the thing is that learning a dynamic model that can precisely predict this transition, that's a difficult problem. And beside that, we need this model to be probabilistic, because if it's not probabilistic, or it doesn't give us any notion of uncertainty, then we don't know when the model is sure and then when the model is not sure. Let's say that you don't have data for a part of the state and action space, but then if you query the model on those part of the state, the space, it still gives you something. But those predictions are completely wrong because you don't have any data there. As a result, in order to trust the output of the dynamic model, you have to have a notion of uncertainty, how uncertain the model is about this prediction. And learning that uncertainty is it's much more challenging problem. And sometimes, because you can't really learn a good measure of uncertainty of the model, then the performance of your policy is typically worse when compared to the other method that I'm just introducing here. I'm hoping this is a bit more clear now.
Yeah, and I also realized that in the previous slide, it's not conditioned on the, I understand the difference. Like it's just an autoencoder. It's not auto-regressively predicting the next state. It's just, yeah.
May I ask another question? I'm not sure why in the right-hand side, with the implicit policy constraint, all the actions are in the behavioral policy, but because they are also generated from when you learn the distribution, you generate some samples, and they could be some of them cause some going out of the policy. So
basically,
yeah, I'm not sure why, because it depends on the probability, as you said. Yeah.
Right. But the important point here to consider is that we are explicitly training a generative model to generate data that are in our database. So again,
Yes.
This is true that, let me just go back to here because it's a quite important question. Maybe some of the faces that you see here, I would say a lot of them do not exist in our training data set. But still, the thing is that you're just interpolating between two solutions, and you're expecting that somehow this kind of interpolation should be all right, because you're assuming some sort of smoothness and continuity for your function that you're trying to approximate here. So again, this is very true that there's no guarantee.
That's what I'm saying.
Yeah, there's no guarantee. That is correct. But it is still way better than this kind of constraint, because I mean, this figure, it's intentionally showing that, okay, if even if you're trying to force the two distribution to be close, there is still some possibility that you're choosing action that are not in the behavioral policies. And I kind of agree with this. And but again, I don't really say that there is like 100% guarantee that if you produce something by generative model, that must 100% of the time land in the behavior, the space of actions produced by the behavior policy. So that's not the case. But this this constraint is better implemented by generative models, in my opinion. I actually did a follow-up research on this topic, and we managed to show that if you do so, basically you can get the best performance and much better than any other algorithm. And one of the main reasons is probably because of the fact that you can constrain your policy in a very good way.
Yeah, but at the end, the train, it is the train policy, it's agent policy as you have here, and this is different from the behavioral policy, and you have to try to make them as close as possible from your loss function. So you cannot. From my understanding from this figure is that from explicit policy you get different policies that you're trying to make them as close as possible, but in the implicit policy you always in place. But is that the case, or is the same similar to the explicit policy?
As I said, that there's still a possibility that you're generating some actions here, but let me just go to the next slide, because I guess that would probably answer your question. Here, that's actually something I guess quite important that you need to consider in this particular example. Here, our policy, the entire policy is like whatever which is contained here. And this entire policy consists of the generative model and something that are called it sub-policy, but other people sometimes also call it, I don't know, high-level policy, or they're just different latent policy. They're different names to this. Here I call it sub-policy. First of all, note that our general policy is the combination of generative model and the sub-policy. The generative model is responsible to map a Z to actions. And you're right that it's still possible for some Z, we are able to generate actions that may not be, that may be out of distribution. So this is still a possibility. But the good thing here is that we have the possibility to optimize this sub-policy here to choose which Z should be generated and given to the generative model to produce the final action. So we have basically another policy network or sub-policy network that we can still optimize in order to regulate this generative process. And another thing that I would need to mention here, if you remember, I told you that we have a constraint when you're using VAEs, variational autoencoders. We have a constraint on the latent space, which force the distribution of the latent variables to follow a zero mean Gaussian distribution with standard deviation equal to 1. So this is a very important property here. Based on our experiment, we showed that if you force the sub-policy to produce latent outputs that are close to the origin. So basically, it's like to generate a truncated Gaussian as the output here. So you don't let it to be like a very large Z. Then you can kind of be more sure that the actions that you're generating here are inside the distribution. And if you don't limit the Z here, so let's say that you let the Z to be like 100, then that would create problems. So if you give a Z equal to 100, and 100 here is, to me, is a very large number, because the standard deviation is equal to 1, and you can expect anything above 1.5 or below -1.5 or 2, let's say, is quite large. If you give a very large latent variable here as the input to the generative model, then it's very risky that you can generate some actions that are completely, does not make sense. So that is something you need to take into account when you're training with this architecture. Did I answer your question correctly?
You're going to talk to me or?
Yeah.
Yeah, that's good. Thank you.
Okay.
I'm good.
I guess we only have 1 more minute to finish the lecture today. Maybe the only thing that I want to talk here is that if we train this generative model before the policy training, because this guy is trained using unsupervised learning based on VAE laws. If you train it this one and fixate it, then you can still use policy gradient algorithm in order to compute the gradient of the objective with respect to this sub policy. And yeah, okay, here's just how the gradient can be computed. So you first compute the gradient of the Q function with respect to the action here, and then compute the derivative of this policy with respect to the latent, and multiply it by, okay, this guy, yeah, maybe there's like, sorry, there's a notational difference here. But the main point here is that you can backpropagate the gradient information through the generative model to calculate the updates for the parameters of the sub policy here. This is another approach that tries to combine the weighted advantages that I explained earlier with the idea of generative model. Basically, it learns some weights based on weighted advantages optimization, and uses this weight for learning the low variational lower bound. Okay, maybe I can stop here. This formulation is particularly very interesting for the cases that you would like to learn from heterogeneous data sets that contain a combination of high quality and low quality data from, let's say, multiple different tasks. I think this would be like my talk for today for offline reinforcement learning. I would be happy, I mean, I know that the time, we're already over time, but I would be happy to answer your question if you have any question. And also you can please feel free to leave the meeting if you for any reason you would like to leave, that's okay. But I can stay for 10 more minutes to answer your questions.
I had a thought that what if your data set contains multiple policies?
That's a very good question, because basically this is the algorithm that you can use in these cases. The good thing about this algorithm, or in short LAPO, is that it first learns the advantages of each action, or let's say state and action pair, and construct a weight vector that's if the advantage is high, the weight is also high. But if advantage is low, then the weight is very low, which means that it can select what part of the data, or what part of the data in the data set to use to train the generative model. In this case, your generative model is not able to produce low quality data that exists in the data set. So still your data set can contain heterogeneous data from multiple tasks, from low quality demonstration. But the good thing here is that by this formulation, your generative model is only capable of generating high quality actions, and it ignores, or it doesn't ignore, it produces low quality actions with a lower probability. And this would help a lot for this kind of settings.
And does that imply that you have a reward function of your environment?
Yes, this is true. For the given task, you're assuming that you have access to a reward function, and this reward function can be used to relabel all the state action transition in your data set.
Because that's something I was thinking about with the slide that we stayed so long on, that with inverse reinforcement learning and behavioral cloning, one of the common problems that tries to solve is that we don't have we have an ill-defined reward function of our problem space.
Exactly.
But
yeah, here the assumption is that you have access to the reward function.
Okay, thank you.
And that's a very good point. For behavior cloning and inverse reinforcement learning, you don't necessarily need to have access to the reward function. But for offline RL, we need to know the reward function.
I ask another question here?
Sure, please go ahead. I need to just correct myself because I made a mistake. For this setting, we need to know the reward function. Okay, please go ahead.
Yeah, so for the heterogeneous data sets, so I guess for different tasks, the reward function should be different, or they have to like, okay, great.
Yeah.
And then, so I think this slide is very interesting. Will you like introduce in next lecture or something in the future, or you just stop here?
Okay, you want a more explanation?
Yeah, because firstly, I'm interested in this setup, like heterogeneous data set setup, so maybe some motivation about it. And then later on for the figure shows like after the advantage weighting, somehow you change latent space. It makes more sense.
Right.
So this is more interesting.
Definitely it requires a bit more explanation. So the idea with this slide is that, as you see, let's say we have a data set of different tasks. So this is a pushing task. Let's say these are the data for a pushing task. These are the data for grasping. These are the data for opening box. Now your task is to basically object relocation. So simply you can relocate an object two different ways. One is to grasp it and push it, and the other is just to push it. So that is why some of these actions are red, which means that they are both good actions for our task, which is object relocation. So that's why they're red. And for example, for the opening box, there's no relevant action because it's a completely different problem. But okay, that's the picture here. Here it says that if you do it in the action space, if you want to learn a action distribution in the action space, you may have problem because this point is good, this point is good, but the point in between is not good. And if you learn a distribution like this, then it's very likely that you're sampling for these points that are completely out of distribution from the considering the training data set.
Yep.
This picture here, this is class. It says that, okay, we have a lot of different actions that are potentially good for the current task, but if you just train a VAE model without considering without considering the advantages, then we are generating also, we're learning a representation for bad actions and also for the good actions. But this representation basically, as you see, there's no structure in it because there's just the VAE loss only tries to reproduce them. It doesn't really have to do anything with the fact that they're suitable for the task or not. But if you do advantage weighting, the good thing is that you're gonna produce, basically you're gonna somehow group the actions that are good for the task. I mean, the grouping is not really like this. I mean, this figure a little bit misleading, I would say. But still, the great thing here is that it would be like by doing this objective, sampling from this distribution, it would be more likely to produce good action and less likely to produce bad action. So that's, I guess, the thing that we try to demonstrate by this picture. And now here you can basically sample from a wider distribution, which contains a lot of good actions to basically produce actions as a result of your generative model. This class, you don't have this feature, and it would be harder probably to find optimal action in this latent space.
Well, that makes sense. Oh, thank you so much. And there's one following up question is that, does it mean like on the left-hand side, so that those are the data sets we collected before, and then in the middle, that is the data or the environment we are working with? So they may have different reward function or different setup. So maybe we didn't even map this environment in our data sets.
I am not, sorry, I'm not sure that I understood the question, but let me just explain something. Maybe I'm already answering the question. Remember that we are relabeling the transition. The data set contains S, A, and S prime.
Yeah.
We would reuse the reward function for the object relocation and relabel all this S, A, S prime again.
I see.
So that they are all basically labeled or rewarded for.
I see. I see. Thank you. Thank you so much. Excellent. Thank you so much for lecture. Thank you so much for today. That's all from me.
Yeah, thank you so much for attending the lecture.
Ali.
Yes.
Hi. I'm gonna ask. Well, they say that there are no silly questions, so
sure.
I'm gonna do it. When we say that there is a let's go into earthly terms. You are describing each dot in the spaces as possible actions, right? So the red dots are valid actions for our mission in this case, in this sample, and gray ones are not valid for this example.
Right.
Now, my point is this space of actions sufficiently enough great, sufficiently large, in order to have as many as possible actions because it potentially is infinite, the number of actions in this case.
Absolutely.
So you are just choosing from a large database data set a number of possible discrete set of the. That's what you want to make sure you have in advance, right? You have a discrete set of actions from which you can pick and choose randomly pick and choose by the policy.
Right, that's a very good question. So first of all, we're typically in robotic at least work with continuous action spaces, but to try to not limit my talk to robotics and make it as general as possible. So therefore, you can of course consider both continuous and discrete action spaces. One main point here is that we are also trying to construct the data set. It's not only the fact that we are just developing the offline RL algorithm, we're also concerned about the data set quality. So, and we know that if the data set does not include good actions for the current task, so we don't have any chance with offline RL to learn anything meaningful. So that is why, first of all, this example probably is not the best example because it contains opening box and pushing and grasping. Maybe that's not the best example, but we first assume that tasks are somehow have a lot of similarity. you know, there's something we call it action primitives. And you can think about if you push an object, there are some sort of action primitives that will basically make this pushing look like a pushing. And there are lots of action primitives that are shared between different tasks. I mean, maybe I can just find a better example. Sorry, I don't have a very good example yet. But there are these kind of action primitives. Let's say, consider a kitchen environment in which you have to open tap, open, let's say, the door of microwave, close the door, open the cabinets, and many different things. And these are the different tasks. But still, there are some sort of action primitives that are similar in all of those things, hopefully, especially when you consider a robotic arm consisting of 7 joints or 7 degrees of freedom, then there is still some sort of a structure, common structure between these different tasks. So the thing here is that if we assume that we have a large number of data from a lot of different tasks, hopefully we can learn this common structure using these kind of techniques. And basically, if you learn the action primitives, hopefully from one task, these action primitives should be also good for some other task. So you don't need to learn everything from scratch. And another important thing that I forgot to say for today's meeting is that we never just do something offline and let it go. We always have a fine-tuning using reinforcement learning on the downstream task. So if the task is to do object relocation, we will do anyway some online reinforcement learning after we find a good initialization with offline RL. This is actually a very active research. This is my research. This is what I'm working these days on. So how to fine-tune a offline RL algorithm on a downstream task. But this is a very important. So we would like to learn those action primitives from similar tasks. We would like to find better initialization, but still we don't expect everything to be solved provided the offline data set. We can still expect some online adaptation to improve the performance even further, or actually to be able to solve the task. But that can be also seen as a way to speed up the learning process. Is there any other question? All right, if we don't have any other question, I would like to thank you again all for participating in today's lecture and wish you a great day. See you next week. Thank you, bye.